Hello again and welcome to our video solution to problem 4 from Superquiz 1. We are going to prove something about functions in this video. We're going to assume we have two sets A and B and a function f from A to B, a function g from B to A. You remember our precise definition of what that means, right? F is a subset of the Cartesian product of A with B, satisfying certain conditions, namely, for every element in A, there exists a unique element in B associated to that little element A. Okay, so G is also a function, and then we look at the composition, right? Now, if we were drawing this composition out sort of with the usual arrow notation, although I like to do it backward, we say, okay, so you have a set A, and F is a map from A to B. And then G is a map from B to A. And so if you compose those two, you get a map, G composed F, that goes from A to A. All right. I like drawing them sort of right to left because then you see the ordering doesn't change. If you drew it backward, you'll notice that the ordering flip-flops when you go to the composition. Okay, but here's what we actually know is that the composition of G and F is the identity function on A, right? So this is the map that does nothing to elements of A. So this is sometimes denoted ID sub A. There's other notations. But the important thing that we know then is that if I apply G composed F to some element A, this is going to equal, well, same thing as if you applied the identity map, and the identity map does nothing. It just sends A back to A. And the goal is to prove that the map here on the right, F, is an injective map. Okay, well, what does it mean to be injective? Right, so F is injective. Well, colloquially, we might say that there are no collisions, right? That is, if you don't have two elements from A which are mapped to the same image. Okay, so F is injective if for all B and B, there exists at most one A in A such that A comma B is an F, or if you prefer, all right, F of A is equal to B. Okay, so these mean the same thing. All right, now that's the strict definition. A very handy way to prove that a function is injective is to assume that you have a collision and show that actually they were really coming from the same points, right? So we're going to assume that you have two elements of A, let's call it X and Y, such that F of X is equal to F of Y. So we're assuming that we have a collision. We have two elements in A, and we're assuming that they're mapped to the same point. F of X equals F of Y. What we need to show is that actually there was no collision at all, that X is equal to Y. So we want to show X equals Y. Okay, so we'll have no collisions. Okay, well, what are we going to do? Well, we know F of X is equal to F of Y. We also, though, know that if I compose G with F, I get the identity map. So let's start with X. I know that X is what I get if I apply the identity map to X. Okay, but the identity map is the same thing as applying G composed F to X. Okay, well, what does it mean to apply G composed F to X? This means I apply G to F of X. And here's where the magic happens. I know that F of X is equal to F of Y, right? That was the assumption. I have a collision. And so I can replace the F of X here with F of Y. So I get G of F of Y. And now all I have to do is unravel this, right? I just basically repeat everything, but with Y's instead of X's. So G of F of Y is the same thing as G composed F applied to Y. But G composed F is the identity map. So this is the identity map applied to Y. But the identity map applied to Y is equal to Y. And so if we read from the left to the right, we start with X, we end with Y, there's equals in the middle. So therefore, X is equal to Y. And because we showed any possible collision isn't one, right? If you had any possible collision, which is what this is, they actually needed to be the same points from the beginning. This implies F is injective, which is the goal of the problem. Now, a good follow-up to this question is to ask, well, is there anything special we can say about this G, right? We know that if G composed F is the identity, that F is injective. Is there anything special we can say about G? So here is an exercise as a follow-up. Prove that G is surjective. All right, so give that a try. All right, we'll see you next time.